Following that week is the typical is the scheduled Northwestern exam week. We are going to ignore completely the Northwestern exam schedule and do basically the same thing that we did for the midterm. Part of the reason for that is because the Northwestern exam schedule only allows 2 hours for the final, and you guys really appreciated the extra time, I think, this for the midterm. Another reason is that I hear that the kinetics exam and the fluids exam would be scheduled on the same day if we were to do that. Is kinetics following the giving the exam as scheduled? Is that correct? Okay, cool. And so we will find some other time to do it. Probably again some evening, and it'll be run very similarly.
Thank you.
Yeah, no problem.
Thank you.
Homework 8 is due on Wednesday of next week, even though there is no class planned. It's going to cover basically the rest of the material. I think most of the problems on homework 8 you are able to do already, just using what you know already with boundary layer stuff, or at least from what we will finish today. There's going to be one problem on there about creeping flow, and so we'll get to that towards the end, hopefully, of today, and then we'll start to get into that a little bit more on Monday. Okay. Office hour schedule as normal next week. Did any of you guys go to Jonathan's office hours this week? Okay, he was probably kind of quiet. Very few of you came to my office hours. Next week we'll have normal office hours, and so I imagine we'll have a lot of homework 8 questions. And the following week we'll also do a normal set of office hours. One of those office hours will probably be like a review session that either I or Jonathan will take care of. Okay. Cool. All right. Well, I guess if there are any questions or anything, I'd be happy to take them. Otherwise, I will go ahead and continue with the material. Let me start sharing my screen. So this is where we left off. We've been talking about boundary layer theory, right? Just to, again, review very quickly. This is what happens when we start looking at flow profiles near a boundary in the singular perturbation case, right? Far enough away, you can completely neglect the effects of viscosity, but when you're close to the surface of a boundary, then you have to deal with both viscosity and inertia in order to satisfy the no-slip boundary condition. Because again, in singular perturbation, when you're far away from a boundary, you cannot satisfy all the boundary conditions, right? We had talked earlier about this sort of flow past a flat plate thing, and then figured out what the solution would be. And then on Wednesday, we started to get into what happens in more complicated scenarios. Specifically, the flow past a flat plate was a very simplified scenario where the flow is uniform, or the inviscid flow solution is uniform. Velocity is just always moving in one direction, right? And the pressure gradient is also nil. So the pressure is just always constant throughout the entire boundary layer. In the boundary layer equations, of course, we learn that the pressure does not change when you move across the boundary, in this case in Y, right? But what does become important, and we started talking about this on Wednesday, is when the pressure gradient actually changes along the boundary layer. And that's what could potentially happen when the flow when the velocity changes, and because, as you know, when the velocity changes, then the pressure changes according to Bernoulli's equation in inviscid flow, right? And so we talked about this planar stagnation flow case, where the flow is coming in from the top, and then by definition, or the result of this, when you apply Bernoulli's equation, is that you have high pressure here at the stagnation point and low pressure here, because here you have low fluid velocity and here you have high fluid velocity, right? And we did some similarity solutions and stuff like that, and got to this really interesting result, where basically our similarity variable, it does not actually depend on, or it only depends on Y, and does not actually depend on X. So what that implied then is that the boundary layer actually does not change in thickness as you move along the boundary layer. Okay. Instead, what you get is just that while the flow just scales, like the flow just gets larger as you move along the boundary, because the inviscid flow, like the free stream flow, the flow outside the boundary layer, also gets larger, right? But the thickness itself doesn't change at all. And the reason why this happens is because of something called a favorable pressure gradient. In this case, we have a pressure gradient where the fluid is moving from an area of an area of high pressure to an area of low pressure. And when that happens, then you have this phenomenon where the boundary layer is thinner than what you might expect. The neutral case is in the flow past a flat plate, where the boundary layer increases with square root of x, right? in this case, because you're moving down a favorable pressure gradient, then the boundary layer grows much more slowly than this as well. Okay. Another way of thinking about it is that while this happens because you have fluid coming down from the top, and the fluid coming down actually counteracts the diffusion momentum that would cause the boundary layer to increase in thickness. Okay. And so the opposite scenario of a favorable pressure gradient is perhaps a word that you guys, or is perhaps something that you guys would imagine would be called instead an adverse pressure gradient. Okay. This is when a boundary layer moves, or fluid in a boundary layer moves from an area of low to high pressure. Okay, and basically what we have is the opposite. So the now the boundary layer becomes relatively thick. It becomes thicker than what one might expect. Okay. So what we have is basically the boundary layer gets thicker until it eventually separates. Okay, and so I wanted to just examine this a little bit more today. There's not going to be a lot of math involved in this also, because like this boundary layer separation stuff is a very unstable problem. As a substitute, hopefully many or all of you guys have had a chance to watch the video that I sent out, and it actually shows some really nice visualizations of what happens when you have flow in a favorable or adverse boundary layer scenario, a favorable adverse pressure gradient scenario. Okay, I will apply it to a scenario that we've talked about already. So let's look at boundary layers in the flow past a cylinder case. The reason is just because this calls back a little bit what we talked about in viscid rotational flow, right? Remember in viscid rotational flow, we use the potential function, and actually we're able to write down the exact solution for what inviscid flow would be past a cylinder. Okay, that inviscid flow solution, at least towards the front of the cylinder, looks something like this. I'll try and do a better job when I draw that. It looks something like this, right? The streamlines would come in like this. Okay. Now, from what we know now about boundary layers, you know that there's going to be some sort of boundary layer that forms near the surface of the cylinder. And that boundary layer is going to have flow that's qualitatively different than the inviscid flow solution, right? And we have a little bit of a clue of what this is. In homework 8, actually, you're going to be asked to examine some of the regions of this flow. Let me go ahead and number those regions. I'll call this point right here number 1. This point over here is going to be number 2. The 2 is supposed to be sort of more at like 10 or 11 o'clock or something like that. Okay, and then at, let's say 2 o'clock, I'll put region 3 right here. Okay, the reason why we want to do this is because we can look at the pressure from the inviscid flow solution. Okay, you guys might recall when we were doing this, problem and actually solving for pressure along the boundary, we were able to actually draw what that pressure looked like, and we actually were even able to plot it a little bit in MATLAB, right? But the pressure along the surface looked something like this. It looked like I have really bad drawing normally and even worse on a touch screen. Okay, it looks something like this. This up here is the front, and here was the back. Right? Excuse me. And remember, this was where the boundary layer, this was where the inviscid flow solution just stopped making sense. because in inviscid flow, remember, there's no viscous drag, obviously viscosity is 0, and so you can't just use Newton's law of viscosity because mu is always equal to 0, right? And so the only drag force comes about from the pressure, and if you have the exact same pressure as you do in the front as you do in the back, then therefore there's going to be no drag, and that was that paradox that we talked about, Deligne-Behr's paradox, right? Well, this gives us a pressure along the boundary layer where we can start to look at whether certain regions are favorable or unfavorable, right? So on this little map that we've drawn for ourselves, this right here is region 1, right? Region 2 comes about somewhere right here, and region 3 is somewhere over here, right? And so in region 1, what we have is basically stagnation point flow. Okay. And in fact, homework 8 is going to ask you to look a little bit, to look a little bit more closely in this region and see how good of an approximation that is, right? But again, we've talked about stagnation point flow. That's basically just this, right? And so the boundary layer flow profiles and everything should look exactly like what we saw out there. Okay. In region 2, you guys just hear a bunch of splashing over there. Oh, you didn't? Okay, cool. My microphone isn't too bad. My turtles are going crazy over there. They're like biting each other and fighting and stuff. Anyway, all right, here we go. Region number 2. In this region, we have pressure going down, right? We're going from an area of high pressure to an area of low pressure. Okay. And so what we have is that the free stream flow accelerates. Okay. And what we have is a favorable pressure gradient. And so this is basically the scenario that we laid out earlier, right? And so what we have is basically a relatively thin boundary layer. Okay. Now, region 3 is where things start to look qualitatively different. Okay. In region 3, we have basically an adverse pressure gradient, right? Because now the fluid is forced to move from an area of low pressure, relatively low pressure here, into an area of high pressure. Okay. And this happens because the inviscid flow actually slows down, right? We saw that in when we were plotting our vector map, right? We saw really large arrows here and then smaller and smaller and smaller arrows here. Okay. And so essentially what we get is that the boundary layer is going to get thicker, and then we're eventually going to see boundary layer separation. Let me actually draw what that would look like. So if I'm going to zoom in to the top of that cylinder, okay, maybe region 2, like I said, 10 or 11 o'clock is somewhere over somewhere over here, and region 3 is somewhere over here where it's like 2 o'clock or something, right? Now, of course, what we had is we have a region of low pressure here. This was the lowest pressure. This corresponds to this point right here. And according to the inviscid flow solutions, we have high pressure on the two sides, right? And so if we have a boundary layer that looks like, let's say something like this, we would expect that the boundary layer should get thinner up here, okay? And we could maybe imagine what the flows would actually look like. Over here, you have the standard boundary layer idea. But once, or this is the standard sort of boundary layer flow like this, right? But once you start to move past this region of low pressure, it's as if you have fluid moving in one direction, but the pressure gradient is fighting you, right? And so the flow profiles might start to look a little bit more like this. Trying to make it a little bit more subtle here, but hopefully you can see that the shape here looks a little different than that. That's actually intentional. That's not just me being a bad artist. Okay. And then when you start to get over here, it becomes even more apparent. Imagine what you would get if you took this guy right here and added it to a parabolic pressure-driven flow, but in the opposite direction, right? Eventually, it's going to start to look like this, like that. And this is boundary layer separation. Okay, and the reason is because in region 3, the fluid does not have enough momentum to overcome the pressure gradient. Okay. And this backflow is when we start getting boundary layer separation. Okay, and so let me just write an adverse gradient eventually causes backflow and boundary layer separation. And once you have boundary layer separation, then you actually just lose the qualitative phenomenon that inviscid flow suggests, right? Over here, we can still match the inviscid flow profile up here. Okay. Now, of course, near the boundary, that inviscid flow profile goes out the window. And so we have to do all the stuff we're dealing with boundary layer theory, right? But once you have boundary layer separation, there's not even any sort of flow in the boundary layer that you can use to match the inviscid flow, the outer flow profile, right? And so then the outer flow profile just becomes invalid as well. And then you see these sorts of real, you see the real sorts of flow profiles that you would see behind a cylinder, where you have like this wake and eddies and stuff like that. That would happen if you were to do flow past a cylinder. Okay. So I'll just say after separation, we need a new description of the flow even outside of the boundary layer. Okay. For instance, the inviscid flow, as we know here from the inviscid flow profile for flow past a cylinder, has high pressures here and here. That's what we drew here, right? And that's what gave us the fact that there was no drag, right? In real life, the actual pressure behind a cylinder is actually much lower than what we have here. And that's just because the flow back here is not what we would calculate from inviscid rotational flow anymore. Okay. So I'll just say, for example, the pressure is actually low in the back.
Actually, I have a quick question.
Yeah.
So given that like you said that this high pressure doesn't actually develop in the back, is the separation of boundary layers like a real thing that's ever observed, or is it just an indication that your theoretical setup is like basically doesn't reflect reality?
Both the things you said are correct. Yeah, I mean the boundary layer separation does happen. You can see it. So watch that video and you'll see actual like boundary layer separation. And what that also means is that your theoretical, when you say theoretical, I think what you actually mean is the inviscid flow profile is actually not valid anymore. We knew that the inviscid flow profile was never actually valid. We just used it as an approximation far enough away from a boundary. What I'm saying is that after boundary layer separation, you can't even use that approximation anymore.
That makes sense. Thanks.
I also had a question.
Yeah, go ahead, Nikhil.
So in the exam problem that you gave out, like for the first exam, there was like the flow through like the channel that was like tape, or like that had like a protrusion.
Yes.
Right? And then when you were describing the velocity profile, you said that like eventually it kind of follows a similar form, like a similar profile that we saw like over here in the flow past the cylinder, right? Like the farther left you go, it starts to kind of look like a helix, I don't know, in a way, right? Like I understand that it was for it was just like a normal viscous flow problem, but was that also attributed to boundary layer separation?
I'll just answer quickly. I'll say no, but I think because very few people on the call actually remember what that problem was, I won't go into too much detail on that. What I'll say is that no, it has nothing to do with boundary layers, because that problem was only like, very thin conditions, low Reynolds number flow and stuff like that. It looked qualitatively maybe a little similar to what I'm drawing here, and that might be what's jogging your memory, but that's because under certain scenarios or like under certain sides of that tapered channel, you were actually having flow moving in or flow moving up a pressure gradient, basically, and that's essentially what you would get. The reason why you see that here is that basically what we're doing is we're taking this normal boundary layer theory, or this normal boundary layer flow, and actually adding it to a parabola going in the opposite direction. And you can imagine that if that parabola gets too large, then the parabola starts to overcome this, right? What we're saying is, just very, very, very briefly, this is what a normal boundary layer flow profile looks like, right? And if we have a pressure-driven flow from this side to this side, then, let's just say a pipe flow or something, that would look something like this, right? It'd look parabolic in the other direction, right? And if you add those together, then eventually you're going to get something that looks like this. Okay.
So the boundary layer theory pretty much only applies for viscous or for inviscid flow problems, or
it only applies near the boundary, in an inviscid flow profile. Yes.
Okay.
Yes.
So like at like some low Reynolds number problem, like we can't use boundary layer theory.
Sure.
Okay. Thank you.
Okay, let me actually do just a couple more examples besides just the flow past cylinder. So I'll just say a few more examples. If you have not watched the video that I sent out, I highly encourage you to do so. It really helps you visualize some of these things. I'll talk about just a couple of those examples. So for instance, in the video, it talked a little bit about diffusers. It's basically just, you can envision this as two plates where the flow could come from this direction. And then by conservation of mass, obviously the flow has to slow down, right? Because there's more area over here. Okay. And what you saw in that was that you have boundary layer separation. If the divergence angle is too large. Okay. This is the diffuser from the video. And the key clue to that is that, well, like I said, by conservation of mass reasons, the flow has to slow down. Therefore, we're going from an area of low pressure to high pressure. And if the pressure gradient is too adverse, then you're going to get boundary layer separation. And you saw that in the video. It visualized it very easily, basically. Like you actually saw backflow in certain regions and stuff like that. Okay. This is actually sort of a sub-example of this is a more general case where you have flow past a wedge. Okay. If this angle, this wedge angle right here, we can call this beta pi. Then we can actually solve for the, you can use complex analysis, for instance. You can solve for the flow profile in the inviscid case exactly. So let me just title this flow past a wedge. Okay. And the free stream velocity, or the inviscid solution, is proportional to x to the power of m, where m can be related to beta, according to this. Okay. The flow past a flat plate scenario is actually just a sub-example, is just a special case of this. Okay. Where beta here is equal to 0. And so if beta is equal to 0, then m is also equal to 0. And so then the free stream velocity is just uniform. Okay. I'll note that beta can be negative. If that's the case, then we're talking about if m is less than 0, then what we're talking about is a case like this. Where the flow has to go around a bend like this. Okay. And if m is less than 0, then, well, what you might expect is, because it's a negative, the power is negative here, then velocity actually decreases over x as x increases, right? So then the flow decelerates. Okay. This is a boundary layer analysis that's pretty famous. It's been done before. I won't get into it, but I will refer you to where it shows up in the book. It's something called the Faulkner-Skan equation. S-K-A-N. That basically describes the flow profile inside this boundary layer. You can look in Dean and you'll see it. In the red edition, it's page 381. Okay. And one of the key conclusions that that the Faulkner-Skan analysis shows is that if beta becomes too small, something like 0.199, this results in boundary layer separation. Okay. And so what this suggests is that you can have an adverse pressure gradient and not have boundary layer separation. Like beta can be a little small, or it can be negative, and the flow can slow down a little bit, and you can still not have boundary layer separation. And from a design perspective, boundary layer separation is bad because that makes it so that the pressure, for instance, behind the cylinder is no longer going to be high, and you're going to have really high drag, right? And so this is exactly why people that work in the aerodynamics industry design airfoils that look like this. Because the streamlines past an airfoil look like this, and specifically are trying to avoid boundary layers separation. In flow past a cylinder, you are going to get boundary layer separation afterwards. And it's just because when you have flow past a cylinder, in this 3 region, it's just too high of a pressure gradient. It's just not going to be able to get, the boundary layer is not going to be able to get up that pressure gradient without separating. Okay. Instead, for this airfoil, okay, if you were to plot the pressure along the airfoil in the same way that we did for the cylinder, that pressure in the front looks qualitatively the same as what we had before in the cylinder case, but because it's tapered towards the back, then the pressure goes up much, much more slowly. Okay. So what I'll say here is if the pressure gradient is too steep, come on, there we go. Gradient is too steep, then the boundary layer separation gives lots of drag. Okay. And so this is why airfoils are tapered, specifically so that the pressure is actually able to go up without getting boundary layer separation. Okay. All right, those are all the examples I want to talk about when it comes to boundary layer separation. And at this point, actually, I've basically said all I really want to say when it comes to boundary layers, and I just want to summarize a little bit. Summary of boundary layer. Okay, so basically what we have found is that boundary layer theory recovers the effects of viscosity and the no slip condition. Right? If you recall, when we were dealing with inviscid irrotational flow, we completely ignored both of these, right? And in so doing, it creates shear stress and what we started calling friction drag. In other words, in the scenario of flow moving past an object, this is like the drag that specifically you get if you were to plot or calculate the shear stress and integrate that. Okay, this comes about directly from viscosity. Okay, the separation of boundary layers that's what creates a wake. Where the pressure behind an object is less than in the front. Okay, this gives form drag. Okay, and so this is how these two new sources of drag, the imbalance of pressure and the friction drag, is what satisfies or what resolves that paradox, right? Okay. And the last thing I just want you guys to appreciate is that the behavior when mu approaches 0 is qualitatively different than when mu equals 0, right? Okay. And this is a consequence of basically applying singular perturbation to the Navier-Stokes equations. Okay. As we said, when mu actually equals 0, then you can't satisfy no sub-boundary condition. There's no shear stresses at all and stuff like that. But then when mu approaches 0, then you have to deal with all this boundary layer theory and stuff like that. Okay. So this is a consequence of singular handwriting's terrible. Perturbation analysis. Okay. All right, and so that's actually all I wanted to talk about when it came to large Reynolds number stuff. I have about 1.3 lectures remaining or something, and so now I'm going to talk about the other side of Navier-Stokes. And that side is a low Reynolds number case. And that's what we like to call creeping flow. Okay. This is maybe mathematically a little bit easier and has some kind of interesting features. So when the Reynolds number is much, much less than 1, then we can neglect the inertial terms of the Navier-Stokes equations, right? To be more precise, what we're actually doing is looking at a regular perturbation analysis of the Navier-Stokes equations, right? And if we completely neglect the inertial terms, then we're looking at the order of Reynolds number to the 0 solution, right? So in other words, we are doing a regular perturbation analysis right? So now let's look at this equation. Okay. In this equation, what we get is basically this. And I guess I should underline this because it's theoretically a vector equation. Okay. And it's a regular perturbation analysis because if we were to express this in terms of Reynolds number, you can go back to when we started talking about how to scale the Navier-Stokes equations. If you recall, there was a Reynolds number in front of all the inertial terms. And if we were to match all the Reynolds number to the 0 power, then this Reynolds number in front of the inertial terms would then get matched to the next Reynolds number to the first equation rather than what we have over here. Okay. This equation is actually called Stokes equation. Right here. And then, of course, you can't forget about the continuity equation. Okay. The phenomena here are a little bit different. Mathematically, I'm not sure it's that much easier to deal with, but it is interesting in that the equations are linear, right? And so all the stuff we were talking about prior to exam 1, for instance, actually used some form of this equation. It was an even easier form than this equation because we typically dealt with unidirectional flow, right? And unidirectional flow, the inertial terms actually just canceled out for other reasons, for geometric reasons, right? But it's basically a subset of this particular equation. Okay, so mathematically, you guys have actually already have a little bit of experience with how to deal with creeping flow. Okay, now physically, there are consequences to the fact that these equations are linear, right? So I'll say this leads to some interesting properties. So before I dive into I'm not sure if I'll have time today to dive into it, but I'll try. Before I dive into the mathematics of some creeping flow examples, let me actually look at some of these properties. Okay. What this means is that given the typical no-slip boundary conditions, right, which basically say that the velocity is equal to 0 at some of the boundaries, right? What this means, or the linearity of the Navier-Stokes equations, means that if some velocity and pressure fields is a solution, then some linear factor, which I'll call alpha times V and alpha times P, these are also solutions. Okay. You can also like add two flows together and stuff like that. And so we kind of implicitly thought about this a little bit when we were dealing with the FFT case, right? When we were talking about like, you know, you have a transient and a steady state solution, you add those together. You guys had a homework problem on that, if you recall, right? As long as you satisfy the boundary conditions, and because in many cases we're talking about no-slip boundary conditions and the velocity is then equal to 0, then you should be able to just add velocities together or multiply velocities by some prefactor, and you know 0 times some prefactor is also equal to 0, and so it all works out basically, right? We've been talking previously a lot about flow past an object. So I'll just say for flow past an object, let's say that flow has a velocity of u infinity, right? Then what that means is that the velocity has to be proportional to u infinity, right? Everything's linear, so everything has to be linearly proportional, right? And the pressure is also going to be proportional to u infinity, right? And of course, what actually defines the drag force then is some combination of the form drag. So if you were to integrate the pressure across the surface of the object, and the viscous drag. So if you were going to integrate the shear stresses, which come about from the derivative of velocity. And both of those things are linearly proportional to u infinity. And so therefore, the drag force we can call that F is also therefore proportional to u infinity. Okay. This is qualitatively different than the inviscid flow scenario, right? In the inviscid flow scenario, you know, with boundary layers and stuff, a lot of times you get something like a u squared or something, right? If you recall, the pressure typically scales as 1/2 rho u squared. Okay. Let me actually draw a few scenarios here. Let's say I have an object that looks like this. And the velocity comes in from the left. Then, as you might expect, and you would be correct, you would think that there's going to be some velocity, that there's going to be some drag force moving in this direction, right? This implies from linearity that if I were to reverse the direction of the flow, in other words, I multiply my entire velocity profile by -1, then that's an equally valid solution, right? And as a result, I can also multiply my drag force by a factor of -1. And so, let me see, let me try and be fancy here. Copy and paste. Then if I were to have exactly the same object over here, but now think about the velocity coming in from this side, then the force should now be moving in this direction, or should now be pointing in that direction. And it should have exactly the same magnitude as this force, right? And so perhaps you can see that this scenario that I've drawn here is exactly identical to this scenario. Okay. So in all of these pictures that I've drawn, the forces are all exactly the same. The magnitudes are all exactly the same, right? And so maybe this is sort of counterintuitive. I hope it actually is, right? What we're saying is that in creeping flow, if I have flow moving, I don't have a wedge here. If I have flow, moving into the sharp pointy end of a wedge, that gives me exactly the same drag force as if I were to take the wedge and then flip it 180 degrees, right? That's pretty weird, right? When you're designing something, when we just talked about airfoils and something, right? Like when you're designing something, you want to make it look aerodynamic. You would be the worst aeronautical engineer in the world if you were to design an airplane wing that looked like this, where you have the blunt end moving forward, right? But in creeping flow, it doesn't matter. They have exactly the same drag forces, right? And so I happen to draw this for a triangle just because, it's completely ridiculous to, flow something into the blunt end of the triangle. But basically this phenomenon happens regardless of shape. Right. Basically that the drag force doesn't matter whether the fluid is moving towards the front or the back of the object. Okay. If we have a symmetric object, so let me try and draw sort of a symmetric ellipse like this. Okay. We have some velocity coming in at u infinity. I'll call this over here scenario A. And this is going to be, whoops. This point right here is going to be point 1. This point is going to be point 2. This point is going to be point 3. Okay. By linearity, if this is a valid flow profile, then crap. Okay, that doesn't work. Copy paste. All right, here we go. Then you could think about velocity coming in from the other side as basically if I were to just take that original velocity profile and multiply it by -1. Okay, we can call this over here scenario B. Okay. And so mathematically what I'm saying is that the velocity far away from an object in scenario B is just -1 times the same scenario in, or times the same velocity in scenario A. Okay. So what that suggests is that the pressure at point 1 in B is also going to be exactly the opposite of the pressure at point 1 in scenario A, right? If I multiplied the velocities by -1, then I should be able to multiply the pressures and get the same thing, right? Likewise, the pressure at point 2 is also going to be exactly the opposite in scenario B versus A, right? But that leads to some interesting conclusions here. Because this object here is symmetric, front and back, then point 3 is the same as point 1 over here in this scenario, right? And so if P1B and negative P1 is equal to negative P1A, then what that suggests is that P3A is equal to negative P1A, right? Does that kind of make sense? So in other words, the pressure in the back is exactly the opposite of the pressure in the front, right? And maybe even more interesting, right here, pressure at 2A, the pressure at this point has to be exactly the same as the pressure at this point, right? So pressure at 2A is the same as the pressure. All I did was basically just take this whole thing and do a mirror image of itself. Okay. And because we showed above right here that this pressure is going to be exactly -1 times this pressure, then the only way that something can be equal to the opposite of itself is if it's equal to 0. Okay. So what this suggests is that the pressure distribution around a symmetric object is antisymmetric. Okay. And you can know that just from pure symmetry. You never even have to solve any equations whatsoever. Okay. Last thing, and I only have 5 minutes left. This should hopefully take less than 5 minutes, is that we can also add flows. You guys kind of saw this a little bit, right? We saw this when we were dealing with a steady state in the transient case, right? What this means is that, let's say, if any of you guys are baseball players, I'm not, I'm terrible at baseball. But if any of you guys know anything about baseball, a lot of times in baseball, you throw what's called a curveball, right? So you're throwing a velocity, or you're throwing a ball with some velocity going in this direction, right? And that ball also spins with some angular velocity omega. All right. what's the point of a curveball for those of you that do play baseball? Can you explain to the rest of the class and me? No one here plays baseball.
I don't play it, but I used to watch it. It's basically to make it trickier for a batter to hit because it's not like a straight linear line. Like it's harder to know from where it comes out of the pitcher's hand where it's going to end up.
Yeah, it's a curveball, right? So the ball is going to curve, but before it gets to home plate, right? In other words, there's going to be some force. There's a drag force moving towards the left here because of the ball is moving to the right. So there's going to be a drag force moving to the left. But there's also going to be some sort of force that has to be moving perpendicular to the ball, pointing perpendicular to the ball, that will cause the ball to deflect from its original path, right? What I'm trying to show you right now is that in creeping flow, that can't happen. Because in creeping flow, the flow around this sphere that's moving towards the right and rotating can be described exactly by the sum of the flow around a rotating sphere and a non-rotating sphere that's moving to the right, right? This here is a rotating sphere. If my pen would work. Right? And this here is a translating sphere. Right? It's maybe not too difficult to see that the force in this scenario on the right has to be moving or has to be pointing exactly to the left, right? By symmetry considerations. And the force that's exerted on this ball also, well, actually has to be zero, right? It's just rotating, so there can't be a linear force exerted on the ball anywhere, right? And so the total force from here and here all have to add up to be exactly pointing towards the left, right? So here, this here has no force, and this here has a force going in this direction. And so therefore, in the grand case, the spinning and moving ball, the force has to be only in the left direction. So that means there's no force perpendicular to the motion of the ball, and so there's no curveball. Right.
Could you repeat again why the force is zero in the rotating sphere and to the left for the translating sphere?
Yeah, 1 second. So no curveballs in creeping flow. So what you're saying is this you don't see why the force would be zero? Okay, let's say that the force is non-zero. What direction would it be?
Like, wouldn't there be like a centripetal force or?
Yeah, so like if you think that there's a net force on this ball when it's rotating, what would that force be?
Oh yeah, no, that's because it's always like changing in direction.
Because it's exactly symmetric, right? Yeah. So there can't be a force.
Can you explain what it would do if it wasn't creeping flow?
Yeah, it would. That gets into the Magnus effect and all of that. Like a spinning ball. If you've played tennis, you kind of you give top spin. If you play ping pong, if you've thrown a curveball, then yeah, that's what would happen. In reality, what happens if it's spinning in this direction, then there will be a force pointing in this direction, pointing up. Okay. This goes way beyond what we're actually talking about, but I think if I recall correctly, the reason is because the pressure is a little higher on this side than it is on this side, but I can't remember exactly why. I think it's because the velocity here is a little bit lower than the air velocity is a little bit lower here than it is over here, but I can't remember exactly why. I might have that backwards. But you should look up something called a Magnus effect, and it'll explain why.
So bottom line, those sports would be really boring if we only had creeping
Yeah,
flow.
in fact, a lot of things would be really boring in creeping flow, actually. It's actually non-trivial even to swim in creeping flow because everything's reversible, right? And so if you move If you swim and take a stroke, but then get back to where you started, then by definition, if you had done the opposite, then you would also have not gone anywhere, right? So, yeah.
One could say that is pretty creepy.
I'm gonna end class now. Okay. Cool. See you guys later. See you on Monday.